theorem on the stress tensor. So what Cauchy's theorem effectively says is that it determines the dependence on the normal of the stress vector. This is how it is determined. So we have pointed out that if I take consider forces acting on a certain body of fluid, then I am looking at the stress field of stress vector. By a field, I mean something that's dependent on the spatial location. So I have all these locations on the surface of the volume that is enclosing this body, and so I can take a particular instant of time and a particular location. We pointed out that depending on the orientation of the surface at that point, the stress vector will be different. Right? So if I consider, for instance, another surface enclosing a different region of volume passing through the same point, the stress vectors that is transmitted across the surface at the same point, at the same instant of time, will be different. So it appears that to specify the state of stress at a particular point, at a particular instant of time, we need to specify an infinite number of stress vectors, since an infinite number of surfaces could be imagined passing through that point at infinite arbitrarily different orientation. Right? But however, what Cauchy's theorem says is that at any instant of time and at any given location, I need to know only what are the stress vectors acting on three elements of area having three orientations, and those three orientations, for convenience, is taken to be the orientations given by the normal that is along the coordinate axis. Right? So this is E1. So at this point, I can consider three surface elements which are such that the outward normal to them is along each of the three unit vectors. So if those stress vectors could be known at a particular location, then this equation gives the stress vector along any normal, that is along or transmitted across any area element with an arbitrary normal vector. Okay, so these are the three quantities that I need to know. Once you know them, then if I give n prime, meaning I have to specify what the normal is. Right? So I simply go to this equation. If these three vectors remain the same, all I have to do is substitute the value of the particular normal vector component into this equation. So if I give n double prime, I will do this. If you give n triple prime, I will do this. So three vectors have to be given. So that means a total of 9 elements have to be specified at a given point. These may be regarded as the components of a second order tensor, which would effectively, in a particular coordinate system, have a representation of a 3 by 3 matrix. Right? So that is what we will look at. So 9 elements, you can clearly see there are 3 elements here, there are 3 elements here, there are 3 elements here. So when I write out this in component form, so I'll subtract the dependence on x and t, because they are the same for all the quantities. So this is an arbitrary normal. The first component, that is along the O1 direction. If I write that would simply be n1. Remove the primes for the given normal. which has components n1, n2 and n3 along the chosen coordinate direction. Right? So this will be n1 e1, its first component. So I'm just writing a vector equation in the component form. So I get three equations plus n2 e2, the first component of the e2 vector, plus the second component, the arbitrary n vector would be again n1, 2, what this vector equation actually means. So now these are the 9 elements. You can see that each one of them has 2 indices, right? So DE1, I can have 1, 2 and 3. So this is the first index. I can choose this, right? So the first index could correspond, for instance, to the direction of the normal. There are 3 normals I am considering, E1, E2 and E3. That will be 1. Then the second one is which component? Is it the first component? Is it the second component? Or is it the third component? So I could define the elements of a tensor like this. So not directly proving that this is a second order tensor, but certainly has an representation of a second order tensor. Now, there are 2 conventions possible. Because the choice of I and j is arbitrary. Now, discussing this convention, we will follow convention 1. Dij is defined as Dei j. So the direction of the normal, whether it's E1, E2 or E3, that will be the first index, because there are 9 elements. I can arrange them in terms of 3 rows and 3 columns. So it's open to choice which one I choose as the row index and which one I choose as the column index. So I am choosing it this way, right? The convention 2 would be both of valid conventions. Some books, most of the books use this. The way you write the final equation will slightly differ form. This is the one we will adopt. This is the one that is followed by VSL, Aris, as well as Segen. So all the references that are given to you follow this. So obviously it's natural that we should follow this convention. For the most of the purpose of this course, it will not really even matter what convention you follow, because in most of this course, we will assume that the stress tensor is symmetric. It does not have to be, right? But we will assume that that is the case. So we consider largely only cases that the stress tensor is symmetric. The stress tensor is symmetric, it doesn't matter how you arrange this, right? So now, given this convention 1, how would I write E1? It would be N1. Of course, the first one is very easy to write, because it would be T11. N2. Is it T21 or T12? T21, right? T21 plus N3, T31. Easy to write, right? This would be N1. T12 plus N2, T22 plus N3, T3, and then the third component would be N1, T13 I will let you write what this would look like. It will look different, right? And it will be identical only in case when the stress tensor is symmetric. Now, if I look at this, I can write the arbitrary component I. But I can be either 1, 2, or 3. Can be written as it's a sum, right? Sum j equal to 1 to 3. Nj what? T
TJ
TJI. In the repeated index, J appears clearly. This is why you just write this by the repeated index of dimension. It will simply be NJTJI. Now you can easily prove that in this case would be Tij Nj, the ith component. When you choose the index, it's very important. The moment I have put I here, that means I am referring to a particular component. That means I cannot be used as a summation index in any case on the right hand side. It's very important. I can use J, K, L, M, N, whatever you want. I cannot appear as a summation index. That's very important. You have to remember. So NJTJI is what it is, and this will now lead to a new product, which is the dot product of a vector with a tensor. Right? So this would turn out to be, now I will define a two new operations, which will be the dot product of a vector with a tensor, the second order tensor. So this one, so the moment for convenience, if the net product is a vector of an operation, I will simply write the ith component. There is no point writing all the 3 components, just more per each time. So again, if the net action of a vector or a tensor operation is a tensor, right? For example, we see the gradient of a scalar we have seen is a vector. When we see the gradient of a vector is actually a tensor, second order tensor. So for that I would simply write the ijth element rather than writing all the 9 elements. Right? So once I am giving an arbitrary element of a tensor, you can construct any element that you want. Right? So the ith component of this operation is simply given by aj. Now the vector dotted with the tensor is not the same as the tensor dotted with the vector. The two operations will not give the same quantity. So A, the tensor, is given by Aij, the ith component. This is actually just multiplying. This is what this is. You can very easily verify. I am now writing it as a dot product of a tensor with a vector. It's nothing more than multiplying, right, a vector, pre-multiplying a vector with a tensor. This would be post-multiplying, but you have to take the transpose. I have already written this in one of the earlier classes. This would be the net effect of this would be the transpose of A1, A2, A3 times the matrix A. If I do this, because this is 1 times 3, this is 3 times 3. So the net result would be a 1 times 3. Right? So I have to take the transpose of that. That the ith component will be this. You can easily verify. So if you are taking the vector dotted with the tensor, then you have to pre-multiply the matrix with the vector. So the vector has to be transposed. Right? Because otherwise, if you take the column vector, it is 3 by 1. You cannot multiply a 3 by 3 matrix with that. So you have to take the transpose and do it. So these are operations that you are very well aware of. Right? You certainly know how to do this multiplication. All I am writing it is in the form of a vector and a tensor. Rather than calling it a vector and a matrix, 3 by 3 matrix, and calling it as a second order tensor for reasons which will become clear later. But effectively, that is what it amounts to. So the ith component of this operation is given by this, and I am using J as the summation index in both. Clearly, then this would have to be simply n dotted with t. So from here, I cannot conclude that if I choose this convention, then t n is simply n. I can write it compactly like this. If I choose this convention, then t n is equal to t dotted with n. So we are not going to worry about this convention. We are going to do this. So I am not going to give the proof of the theorem yet because it will take some time and even relegate it to an assignment. Right? But what I want to do is proceed with this. So the significance of this clear. That is what is important to understand. Right? The significance of Cauchy's theorem is that the state of the stress is, so important thing to remember here is this, t of x, t, this is the time, n, is n dotted with t. That doesn't have any normal dependence. Stress tensor does not have a, it's independent of any norm. Because those are the stress, the components of the stress vector, so the chosen normal, so the normal is again taken into account, right? So what this says is that the across any normal, all I have to specify is the stress tensor. So that is dependent only on the position and time, right? Then I perform this operation for any vector. So I can now write it in a compact form. If it is n prime, I will get this. If it is n double prime, I will get this. So I have separated out the normal dependence. Right? And I am getting a tensor as a result. This is somewhat analogous to the mass flux being given by the dot product of a mass flux vector with the normal. Somewhat analogous to that. Because if you see here, there, what we want is a scalar. And that scalar is the result of taking a dot product of a quantity which is a vector, that is one order higher than the scale. The vector can be regarded as actually a first order tensor. Scale is a zeroth order tensor. The order of the quantity is increasing. So if I want the mass flux scalar, then I take a mass flux vector which is independent of n. That's dependent only on the position. We have rho which is a field and b which is a field. In the normal sense, that is dependent only on x and of course time. When I dot it with n, I get the mass flux scalar. Similarly, when I want a vector, which is a stress vector, which is dependent on the normal, I take the dot product of n with the stress tensor. So I know the one higher order quantity. Then I will get the stress vector. Again, this is dependent on the normal. When you take the dot product, so it contains two parts. Where again the dependence of the normal is separated out in this way. You have a quantity which is independent of the normal, the dot product of n. Same thing you are doing here. Yes.
So for example, then we can interpret that. For example, T2, the first, that is n1 dot t, n dot t. That it is a force in the x direction due to momentum transfer in the other direction.
No, we are not looking at momentum transfer here. Basic point is the stress vector can act in any direction. It is not necessarily proportional to the normal as in the hydrostatic case. Right? So if I take a, so this is the, let's say this is the normal. The stress can be anywhere, right? That's what this says, and it says how it depends on the normal. How given the normal, how I can calculate the stress? What is the direction of the stress vector? Right? That relation is given by this. So it requires for you of course to specify the normal, you require also the stress tensor at that point. Right? So what this means really is the state of stress is specified entirely at a given point and at a given instant in time by the stress tensor effectively. Because as I said, the state of stress is specified when I know the stress vector along any normal direction. Right? That is the stress that will be transmitted across a surface area of arbitrary orientation or across a surface of arbitrary orientation passing through that point. And we could have infinite number of them passing through the same point, all with different orientation. So the state of stress at a point is specified only when I know all these vectors. This says that all I have to do is to specify the tensor. Then whatever normal you specify, I can calculate the stress vector. That's all. You will not come to how it is related to the transfer of momentum at this stage. So, are there any questions?
So, in this case, have you taken three different normals, n prime, n double prime?
No. Yes, effectively. The n prime I am taken to be E1, n double prime to be E2, n triple prime to be E3. So, I will reduce the problem to that. So, I will reduce the problem.
So, effectively, n prime, n double prime, and n triple prime, they have to be mutually perpendicular or can be any.
No. If they are mutually perpendicular, and if I know the stress vectors corresponding to that, you cannot get something out of nothing. Right? Cauchy's stress theorem says if I know the stress vectors along three mutually perpendicular directions, that means along where the normal is oriented along three mutually perpendicular directions, if I know the stress vector corresponding to that, right? So what it says, because I said n prime, n double prime, n triple prime can go on for infinite number of normals. Right? But what the Cauchy stress theorem says, E1 take E1, that is n prime equal to E1, n double prime equal to E2, and n triple prime equal to E3. Then find T, right? So you find T E1, T E2, and T E3. That's it, the problem is solved. You tell me that what n 4 minus 5 minus whatever n might be. Obviously, you have to specify its components, whatever it be. So these are the ones that give me the stress tensor. So once I have those 9 values, whatever may be the normal you say, right, of the particular area element passing through that point, I can tell you what the stress, I can calculate what the stress vector is using this relation. So there's no need for any further knowledge to calculate the stress at that point. So this much you have to know, right? Then everything else is determined. All other stress vectors at that point will be determined. Yes.
Just to become so n dot E is for a certain area. The n is the normal to that area.
Yeah, exactly.
E is a point where it will always it is independent of the orientation.
Exactly.
And n dot E from the orientation of the area will get n prime n dot.
Exactly. So this is separated. The dependence in the normal is separated into two parts. One part which is determined by the normal, the other part which is independent of the normal. But for that we need a tensor rather than a vector. Right? So that is the point. So now we get back to the equation of motion. You remember the equation of motion is like this. Right, so we now write the I component, for instance, right? We now write the I. We already said that this can be written as, right? And then I can bring the so I'll write the ith component. The ith component would be rho dt I by dt minus rho bi dt. But one of the problem, I mean, where we started this, I said that as we did for the continuity equation for the mass, right, we start with an equation applied to the body as a whole. The law of mechanics applied to the body of the whole. Right? We've already applied the principle of conservation of mass, right, to the body as a whole. Right? Then we get what is called as a local equation. It is called as continuity equation for mass conservation. And then once you have obtained a local equation, that means an equation that is valid at every point within the fluid, then I can integrate it over any control volume that might be of interest to me and get the control volume equation. Right? So to obtain a local equation, the problem here is this, it is an area integral. So we need to convert this to a volume integral. The first step towards that is a Cauchy stress theorem. So if I were to write the ith component of this would be nj dji dA. Right? Now we have already seen the divergence theorem. You see the power of the divergence theorem, the particular form of the divergence theorem that I wrote down in 7. Right? That will convert any area integral to a volume integral and back and forth. Right? So that is, if you recall, g comma I dV is equal to g ni dA. Right? So now, looking at this, clearly I have nj here. Right? So all I will do is to make it j. So that choice is purely arbitrary. We call it I or j. So now nj is here. So can you tell me what this is now the reverse? We are having an area integral. So clearly very obvious what g is. G is Ej I. Right? So if we were to write this in terms of a volume integral, what would it be? Ej I comma j or I? Just be j, right? It cannot be I because I am looking at the ith component, so I cannot be a summation index. So I have now converted it. However, this is also can be written in the form with all of this in the Cartesian coordinates. This can also be written in terms of the one of the vector or tensor operators. So to add to the two new operations I introduced, the dot product of a tensor with a vector, right? Two possibilities are there. Now I will define what is called as a divergence of a tensor. And we have seen that the divergence of a vector is a scalar. You can easily guess the divergence of a tensor will be a vector, right? Now, for the vector, I will write only the ith component is defined like this: Hi, comma j. So, if you want to write it fully, right? So that could be the ith component. I am writing this the ith component of the vector, right? So that would be dA1 prime by dx1 you can easily verify that I've written the sum correctly. This is the sum over j is understood. So I have write j equal to 1, 2, 3. So I write j equal to 1 dA1 I by dx1. So I can be 1, 2, 3. That's clear, right? An arbitrary component. So if I put I, if I want I equal to 1, I will replace I by 1. So you get 3 components that way. So it is clear then that this is nothing but dV. Right? So I can write the vector equation as, because I've got the I component of this, the I component of this, the I component of this. So I can write the vector equation as rho dv by dt minus rho v minus equal to 0. Because I have achieved what I wanted. I have now converted the area integral also into a volume integral. Towards that, I have first proved the, not I haven't proved it, I have stated the stress theorem, right? So that introduces the stress tensor. Then I have got this into the area integral, then it becomes easy to convert it to a volume integral, right? For that, I have to define a new operation, namely the divergence of a tensor, right? And so once I have that, I can write this as the I component of the divergence of the stress tensor. So I have the I component here, I component here, the I component here also. So I can easily combine and write the vector equation like this. Again, I use the same argument, even though the integral only is 0, right? And this is applied to a region in space which I am now considering as a body of interest. I can now consider smaller and smaller regions, right? And progressively reduce this to the point and then conclude that the whole integrand is 0. So I get the famous Cauchy's equation of motion, which is the units of this is force per unit mass. This is mass per volume. The units for each and every, it's a force balance. After all, that is what it is. Momentum balance is a force balance. The rate of increase, the rate of change of momentum is equal to the net force acting on the body. So it has to be force balance. But because it's a local equation, right, what you're getting is every quantity is a force per volume, right? This clearly is this is somewhat like F equal to ma. If you recall, the velocity was defined as dx by dt. Therefore, the acceleration would be dv by dt. This is a local point. That's the acceleration of a fluid point locally, right? So what this says is the rho times that. So if you recall, ma, this is basically like that. Unfortunately, F as a single scope is the force vector. So now we are using capital letters for the tensor, the double scope, right? So that's not a tensor, it's a force, right? Force equal to dA. But there's a force per unit volume, right? This also has the units of force per unit volume. This also can be regarded as an acceleration per. Not quite. Also has the units of force per unit volume, but this is the acceleration. So instead of mass times acceleration, because everything is per unit volume, you're getting the density, right? Because there's no mass at a given point. The point mass has a mass concentrated at that point. The analogous quantity in continuum mechanics is the density field, right? So if you're talking about a point, right, we cannot talk about the mass. We have to talk only about the density, the mass per point. Actually, mass times acceleration per unit volume. This is the body force per unit volume. This can be regarded as the contact force per unit volume, but it has a very unique feature that is not there in any of the equations of forces of mass point mechanics. It comes as a divergence of the tensor. So while from this you may have predicted at least this part has no analog in mass point mechanics. That is why you have replaced, because this is force, actually, this is the force per unit area. But here, it comes, the local equation, it comes as the divergence of a stress tensor, which would have been very difficult to have imagined just by analogy to mass point mechanics, because there is no analogy in mass point mechanics to this kind of quantity. Right? So you can regard this as a local balance of force, where the mass times acceleration per unit volume is equated to the body force per unit volume plus a quantity which may be regarded as a contact force per unit volume, but it's actually given with the divergence of the stress tensor.
So then we can take the area integral, that is the contact force. So it is the net efflux of the contact force.
No effects of a force. If you mean effects of a momentum, you get a better idea when I know integrate this over a fixed controlled volume. Right? That is the next step. If we follow the line of thought we have adopted for the mass balance, right? Then of course it will be very easy. Because of conservation of mass immediately leads to the continuity equation on the Reynolds transform. Even here you have to prove the stress theorem of Cauchy. So you can reduce it to an equation of motion. Now the question is, I will integrate this over a control volume, right? And then obtain the control volume momentum balance. And there you will get the momentum influx, just as you had an in minus out for the mass, rho v dot n dA. Right? So here you will get that the rate of change of momentum within the body is that sum of the forces plus a term that represents the net effects or influx of momentum. So we will do that in the next step. So if I want the spatial derivatives to come, obviously I have to first reduce this. That's easy to do. So what I will do is, now we will get a formula for the substantial derivative of a vector, right? So I'll explain that will lead to some new operations, further new operations. Now we've already seen df by dt, f is a scalar, is given by df by dt plus but what I have here is dv by dt. V is a vector, right? So now what I could do is apply it first to vi, then I get dvi. Right? But it will turn out that I can simply write the vector itself, that is the substantial derivative vector itself. Same formula to apply, provided I define the gradient of a vector suitably. Right? So now I can write this formula, I haven't proved, right? But if you write it out, I equal to 1, 2, 3 and combine all of them, then you can show that you can write it in this form, provided, now I will introduce another operation. If I can introduce equal to in this class, we will introduce this one, right? The divergence of a tensor. You know, it is the gradient of a vector. So again, the gradient of a scalar is a vector. The gradient of a vector, you can guess, would be a tensor. Right? So the gradient of the divergence of a vector is a scalar. The divergence of a second order tensor is a vector. The same way, the gradient of a scalar will give rise to a vector, and the gradient of a vector, right, can be shown to be a second order tensor. We are not going to get into the technical proofs. We simply assume that they are tensors. So I need the I-shaped component. So I do only the I-shaped component rather than writing out the full tensor. Right? It's just a comparison process. This we will now define. It's a dAj by dxi. Of course, you can define it as dAi by dxj also. It's open to choice. But the way we have developed these equations, to be consistent with this formula, right, we have to define it that way. Right? So I can write it in compact form as aj comma I. So now that I have got the tensor, right, so let's now write out what the I component is. I prove that this is justified, and this is consistent with the substantial derivative formula for a scalar that we already have. Right? So now, what you have here is the dot product of a vector with a tensor, but only that the tensor is now formed by another operation, namely the gradient of a vector. Because I have already defined what would be the dot product of the vector with the tensor. But only thing, this tensor is further has to be broken down and it is coming out of the gradient of a vector. So that makes it slightly more difficult to write it. So if I were to write the ith component again, so I get the ith component of this. Right? So what is the ith component of this? So I'll go back to this formula. Ith component of a vector is a tensor. Right? That is Aj. Right? So this will be Bj. Right? Capital Aj. That means the jth component of the tensor. So I will first write it. So you have to be very careful. Sometimes you might see, for instance, here I have defined the ijth element, but what we are actually needing is the jith element. So the table you should know how to use it. Even if I were to give you the table of operation, you should know how to use it properly. Right? For instance, some cases you might require the jth component. You are doing a series of operations and suddenly you want the jth component of A dot A. Then you cannot use this formula directly. If you put Aj, Ajj, that is meaningless. You will then change the summation index to maybe K or I or whatever. Right? You have to be very careful how to use it. So this is the first step. It's directly following from this. Right? So now since I have the ijth element of the gradient of the vector, so jith element, I just have to interchange the indices. Right? So this would be Bj, Bi, comma J. So let us write out what this is. We have run out of time. Right? You can easily write out what this is. This is B1 dBi by dx1 plus B2 dBi by dx2 plus B3 dBi by dx3. That's what it is. Now let us check this. What is this? This is very easy to do. Right? So this is the ith component I written using the formula for the substantial derivative of a scalar. Right? So this is the dot product of a vector with that of another vector. Because I'm doing only the one component. So this is a scalar. The gradient of the scalar is a vector. So this would be, if I want the ith component, that is what I have written. Right? So that would be Bj, right? Bi, comma j, right? Bi, the gradient, would be because it's j, I'm choosing j as the summation index. I cannot choose I. So this is actually A dot B. I can write this as Aj. And because I have already used it, right? So this is a vector B. So Bj times the jth component of the gradient of Bi, right? So that would be Bi comma j. And that is exactly what that dot product is. And clearly, it is exactly what we get by writing it in a slightly different way as the ith component of the dot product of the velocity with the gradient of the velocity, which is a tensor, which is entirely consistent with the original formula, this definition, right? So we continue with this, we run out of time, we continue with this on Tuesday, because Monday is a holiday. So I'll hand over an assignment sheet shortly, because I just waited and we have a sufficient number of these vector and tensor operations. We should get familiar with them. And as of now, for the long weekend, I can only suggest a reading assignment from Aris, the first 3-4 chapters, which discusses all of these operations. Right? So you can go through it and try to solve some of the exercises given there. We'll discuss them in detail in next week.